This instructional video shows the steps how to take a real space structure and convert it into a 1D representation of slit-smeared data as if it was measured on the USANS instrument. To start, from the Macros menu, load the real space modeling routines. This loads in all of the analysis package, which we don't need right now, and the real space modeling panel. To calculate things on the length scales of USANS, we need to increase the number of cells and also increase the length per cell. With these conditions, the length of our box would be about 13 microns per side of the box. And also, the minimum delta Q here is on the order of the resolution of the USANS instrument in the X direction. Of course, in the Y direction, there's very poor resolution. So we generate the matrix, make the gizmo plot. Once that is made, we can retrieve that. And then we can draw a simple spherical structure of, say, a radius of about 1 micron or 10,000 angstroms, and put it somewhere near the center of the box. Once this is drawn, we can then do two different calculations. For USANS sort of calculations, there's two choices. First is ISO, meaning isotropic to USANS. That's if you have a sample where you want to take the object you've drawn, orientationally average it over all orientations, and then calculate what you would see with USANS. This is if you had, say, a structure in solution where you had multiple structures. The second option is anisotropic. That is if you had a sample that had a particular orientation in the beam, like oriented cylinders, flux lattice, or something aligned with a shear cell or similar. In that case, again, you do this calculation. It does the three-dimensional Fourier transform, gets the two-dimensional detector plane out, which in this case is the ZY plane. And this would be the two-dimensional detector image that you would expect to see in a SANS experiment, where you see the anisotropic two-dimensional scattering. But then this anisotropic scattering, since it is USANS, would be collapsed to 1D, where you lose the resolution information in the vertical direction, the Z direction in this case, but still have very good resolution in the Y direction. In this case, if we do the calculations, then since it's a structure that is spherical symmetry, the anisotropic and the isotropic case should be identical. So this will take a few seconds for the calculation. And once this is done, it shows a plot of what the one-dimensional scattering looks like, and also a few graphs. I apologize, there's not a lot of real estate here. This narrow one shows the shows the positive half of the detector as if you would see it in 2 dimensions. In this case, of course, it's isotropic. There are also a few other representations of this, including the full 2-dimensional detector slice on both log and linear scale. If we also plot the Fourier transform result, which was automatically calculated in the process of calculating the USANS result, the upper curve here is as if you took the data with a pinhole camera. That is, there is no slit smearing. So we see there's many more deep fringes that are, of course, smeared out by the slit smearing of USANS, and also the q to the minus 4 dependence of the pinhole data at high Q is now q to the minus 3. The slope is knocked down by a power of 1, which is what we expect. If we do the anisotropic calculation, again, this should take about 10 seconds now, and should be identical since there is no anisotropy in the sample. And that's in fact what we see. Now we can use different sorts of objects like cylinders, something that can be oriented, and I'll show you an example of that. So if we clear this by just refilling the matrix with solvent, and then draw a cylinder pointing in the x direction, which is the beam direction, and we give it a radius of, say, 0.5 micron, and make it, say, 3 microns long. Again, put it in the center. And once we have this structure, if we do the isotropic calculation, this should be the scattering of a cylinder. And that's what we see. It's sort of tending to q to the minus 1 at low q, q to the minus 4 at high q, and this sort of brown curve is, again, tending towards 0 at low q, q to the minus 3 at higher q. If we do the anisotropic case, it won't exactly match the isotropic case, because in this case it's only getting information about the cross-section of the cylinder. In the ZY plane, there's absolutely no information about the length of the cylinder. If we would orient the sample in some way such the length was, at least a projection of the length was in the ZY plane, such as if we rotated it, say 120 degrees around the Z-axis, if we rotated it so that some of the length was actually in the ZY plane, then we would see some features of the length and some features of the radius in the anisotropic scattering. The isotropic calculation, of course, would be the same since it's the same cylinder, and it doesn't matter where it starts when you do the orientational average. This rotation takes a little bit of time. It's actually longer to do this than actually do the Fourier transform calculation. But once this is finished, again, the Fourier transform won't take any longer. Any of these calculations that have been done for the USANS scattering can be calculated, compared directly to a model scattering in these cases of spheres and cylinders. If you load in an example data set of slit-smeared data from the USANS instrument, you can then slit-smear a model calculation, a model sphere calculation, or a model cylinder calculation, and see that for the isotropic case, these real space results do match up with the analytical calculations. But what the difference is here is that if you have something that is oriented in the beam, with the analytical calculation, there's absolutely no way to calculate what you would see with USANS. And in the same way as if you're doing something with a non-traditional sort of geometric structure, something that's very complex in shape, then again, there's no way to do it analytically, but you can do it very easily with real space. And with the cylinder in this orientation, the cylinder is still in the lying in the XY plane, but is now tilted so that part of the projection of the cylinder is in the YZ plane. And what you see now is instead of simply the length scales due to the radius, which show up around this Q value, you have larger oscillations indicating larger length scales, and these are due to the length. You also see this odd peak showing up at high Q, and this is actually one thing you need to be careful with when you're building objects out of sub-objects, is that you can occasionally get artifacts due to the spacing of these cubes, because this actual cylinder is actually made up of cubes all next to each other. And in the original representation when it was drawn, the artifact wasn't there, but simply a consequence of the rotation, sometimes these artifacts will appear. So you do want to be careful and look out for these. But what you see again here is now the scattering of this cylinder that's partly oriented, And you can see this also in the two-dimensional scattering, which, again, this is what you would see on a SANS instrument with pinhole resolution. You now see in the horizontal direction, you see very tight fringes due to the long length scale of the cylinder, not the full length of the cylinder because it is oriented slightly. It's at a 30-degree angle. And then in the vertical direction, you see a wider spaced fringe due to the smaller cross-sectional radius of the cylinder. And this results in this sort of elliptical sort of scattering for this partially oriented cylinder.